Hello everyone. So now that we know what a differential equation is, its definition, and its classification according to its type, degree, and order, we will now learn about the solution of an ordinary differential equation. So as we all know, just a little review, an equation is a mathematical statement showing the equality of two expressions on either side of an equal sign. That's an equal sign. So for example, this one is a linear equation. That is a quadratic equation. And then we have an exponential equation, a logarithmic equation, a trigonometric equation, and a differential equation, showing the equality on either sides of the equal sign. Now, if we are to solve a solution, it means we are finding suitable values for the unknowns which will make the equality true, or in other words, the values for the unknowns which will satisfy the equation. So for example, for this linear equation, its solution is 2 because when you substitute this value of 2 here to the unknown x, 2 times 2 here is 4 plus 3, that is equal to 7 on the right side of the equal sign. And for this one, for the quadratic equation, we have two values of x which will satisfy the equation. We have negative 5 and 2. When we substitute them, it will be equal to 0. And for this one, for the exponential equation, the value of x here is 3. 2 to the power of 3 is equal to 8. So it satisfies the exponential equation. And then for the logarithmic equation, if they take the log of x to the base 2, the answer is equal to 3, and that value of x is 8. Now, for a differential equation, the solution of an ordinary differential equation is a relation, unlike any of those given equations wherein we were given exact values of the unknown. For a differential equation, the solution is a relation, or a class of relations, whether expressed implicitly or explicitly, which again will satisfy the equation. Another definition for it would be is that it is any non-derivative relation among the variables which satisfies the differential equation or can reduce it to an algebraic identity when substituted. So it's like proving an identity wherein you can see that at the end of your solution, you will see that both sides of the equation are equal. And then there are two types of solution for a differential equation. The first one is the general solution. So if you remember your arbitrary constants, it's a set of many solutions. And in a general solution, it contains arbitrary constants, wherein these constants could mean any value. For the other type of solution, we have a particular solution, which is any solution, any one solution, which can be obtained from the general solution. How do we do that? By assigning specific values to the constants. So because we have already assigned specific values to the constants, for a particular solution, you cannot find anymore an arbitrary constant. So for example, for the given differential equation y double prime plus y prime equals 2y, the solution for that is the relation y equals c sub 1 e to the power of x plus c sub 2 e to the power of negative 2x. And how do we know that it is indeed a solution to the differential equation? We are going to substitute this here. But as you can see, the solution is just, a relation. We have y here equals to this. But in the differential equation, we have y double prime and y prime, which requires us to perform differentiation. So we'll get values here of y double prime and y prime. So to be able to prove that this is indeed a solution to the given differential equation, what we do first is we are going to differentiate the given solution twice to get y prime and y double prime. So again, our given solution is the relation y equals c sub 1 e to the power of x plus c sub 2 e to the power of negative 2x. And differentiating, we have y prime equals c sub 1 e to the power of x minus 2 c sub 2 e to the power of negative 2x. And then differentiating again, the first term will still be the same, but the second term will now have a coefficient of positive 4, so plus 4 c sub 2e to the power of negative 2x. So now we have the y to be substituted in the differential equation, and we also have y prime and y double prime. So the next step would be to substitute these to our dE. So substitute the derivatives to the given differential equation. Y double prime plus y prime equals 2y. So our y double prime is c sub 1 e to the power of x plus 4 c sub 2 e to the power of negative 2x, and then add it to the first derivative, c sub 1 e to the power of negative x minus c sub 2 e to the power of negative 2x, and that should be equal to 2y. But we still have to prove that. So combining the similar terms, we have c sub 1 e to the power of x here, and we have another c sub 1 e to the power of x here, that would sum up to 2 c sub 1 e to the power of x. And then we have 4 c sub 2 e to the power of negative 2x here, and then we have a minus 2. So that would give us plus 2 c sub 2 e to the power of negative 2x. And that's supposed to equal to 2y. And so we can see here that the common factor is 2, so we can factor that out. That would give us 2 times the quantity of c sub 1 e to the power of x plus c sub 2 e to the power of negative 2x. And we know from our given that this is just equal to y. And so substituting that, so therefore 2y equals 2y. So when we are substituting our solution to the differential equation, we make sure that we don't transfer terms from the left side to the right side. So we want to prove, so we must, as much as possible, we don't touch one side of the equation, or should you make any operation, should you perform any operation, you must do it exclusively on both sides. So just remember that whatever operation that you do on one side, you must also do it on the other side. So here we just touched the left side of the equation, the more complicated side, and transformed it into the more simple side, 2y on the right side. And so we were able to make an identity, so therefore we conclude that indeed the relation y equals c sub 1 e to the power of x plus c sub 2 e to the power of negative 2x is a solution to the differential equation y double prime plus y prime equals 2y. Another example, we want to prove here that the relation y equals c sub 1 sine 2x plus c sub 2 cosine 2x is a solution to y double prime plus 4y prime equals 0. So as you can see here, we have y double prime and we have y. So we just have y here, but we need y double prime, which means that we have to differentiate the given solution twice to get y double prime. And so differentiating, we have y equals c sub 1 sine 2x plus c sub 2 cosine 2x. So the first derivative is the positive 2 c sub 1 cosine 2x minus 2 c sub 2 sine 2x. And differentiating again to get y double prime, we have negative 4 c sub 1 sine 2x minus 4 c sub 2 cosine 2x. And that's common here is negative 4, so we can factor that out. We get negative 4 times the quantity of c sub 1 sine 2x plus, we just need to erase this part here. There's no more 4 there. That's plus c sub 2 cosine 2x. And so we substitute that to the differential equation. So again, there's no more 4 here. And then plus 4 times the given y, 4 times this one. And that should be equal to 0. So as you can see, this is negative 4 and that's positive 4 here, and the terms inside the parentheses are basically the same, so they cancel, so 0 therefore is equal to 0. And so we conclude that the relation y equals c sub 1 sine 2x plus c sub 2 cosine 2x is a solution to the differential equation y double prime plus 4y equals 0. Okay, another example. We are supposed to prove that the relation dy dx equals x squared of y, and that's our dE, and our solution is y equals 1 over 16x to the power of 4. So we only have dy dx. We are supposed to differentiate it once. So differentiate the given solution. Our given solution is this one. And differentiating, we get 1 over 16 times the quantity of 4x cubed. And when we simplify that, we get 1/4 x cubed. After which, we are going to substitute the derivative to the given differential equation. And here, we are going to work on each side of the equation independently. Remember, we are not supposed to transfer terms from one side of the equation to the other side. So we're going to work on each side of the equation independently. So our given dE is this one, and we are substituting dy dx here, so that would be 1/4 x cubed, and y, as we know from the given, is equal to 1 over 16 x to the power of 4. And extracting the square root here, that would give us 1/4 x squared. And multiplying, 1/4 x cubed is equal to 1/4 x cubed. So we're able to make an identity without, again, we manipulated both sides of the equation, but we didn't transfer any term from one side to the other. It has to be done on each side of the equation independently. And so we were able to make an identity. So we conclude that the given solution, the given relation y equals 1 over 16x to the power of 4 is a solution to the differential equation dy dx equals x square root of y. And so in the next video, we are going to be talking about the elimination of arbitrary constants to solve or to find a differential equation.